In the name of Almighty God, I'm Mahsa Sankosha, and today I want to talk about Introduction to ACDC module in Quantum Multiphysics Simulation Software. Today I want to go to the electrostatics, and now it is time to define the physics settings such as material models, initial conditions, and boundary conditions. In this example, the terminal feature is used to model metal fittings and grading rings at both the line and ground ends. Note that the free space default feature is used to model empty space. It assumes a relative permittivity of 1. You can add more features to override empty space with solids, liquid, or gases. Charge conservation in solids. The first step in the model builder window under component 1, right-click Electrostatics and choose Charge conservation in solids. Select domains 3, 4, 5, and 7 and the core rod and the weather shed. This can be done manually by clicking in the graphics window or by choosing the paste selection option and typing 3, 4, 5, 7 in paste selection dialog. Now I want to go to the metal fitting. In the model builder window under the component 1, right-click Electrostatics and choose Domain Terminal. In the settings window for Domain Terminal, type Metal Fitting Line and in the label text field. Select Domain 2 only, locate the terminal section. From the terminal type list, choose Voltage. In the V0 text field, type VI. The settings are shown in the figure to the right. Next, configure similar settings for the metal fitting at the ground end. Now I want to go to the metal fitting ground end. In the model builder window under component 1, right-click Electrostatics and choose Domain Terminal. In the settings window for a domain terminal, type metal fitting ground end in the label text field. Select domain 6 only, locate the terminal selection section. From the terminal type list, choose voltage. In the V0 text field, type 0. Now I want to go through the materials. Ideally, the metal is an equipotential body and the electric field inside the metal is 0. Usually, the metal parts are excluded from the computation domain since their potential is known in advance. One can also include the metal parts and define the potential using the domain terminal feature. In this case, the domain of the metal parts is not solved, and thus it is not necessary to assign the material to it. For other domains, the relative permittivity of the material needs to be defined as listed below. Core rod, the relative permittivity is 5. Weathershed, the relative permittivity is 3. And air, the relative permittivity value is 1. The first type, core rod. In the model builder window under the component 1, right-click component 1 and materials and choose blank material. In the setting window for material type, in the label text field, select domain 3 to 5 only. An easy way to do this is to first clear the selection and then manually select domains 3 till 5, the core rod. Alternatively, clear the selection. Choose the paste selection option and type 3, 4, 5 in the paste selection dialog. Locate the material contents section in the table. Set the value of relative permittivity to 5. The settings of the core rod material are shown in the figure to the right. Next, add similar settings to other materials. Watershed, right-click Materials and choose Blank Material in the setting window for material type Watershed in the label text field. Select domain 7 only and locate the material contents section in the table. Set the value of relative permittivity to 3. Air type. For the air, the default free space properties will suffice. It is therefore not necessary to add the material properties explicitly. I want to go through the study one and select resulted without grading rings. The first study is study one in the model builder window. Click study one in the setting window for study. Type study one without grading rings in the label text field. In the home toolbar, click compute. The study node automatically defines a solution sequence for simulation based on the selected physics and study type. In this case, the simulation only takes a few seconds to solve. Once it is finished, several default plots will show under the Results node. Results section. In the Model Builder window, expand the results and then select the dataset node. Then click the Study 1 and without grading ring Solution 1. In the Results toolbar, click Attributes and choose Selection. In the Setting window for selection, locate the Geometric Entity Selection section. From the Geometric Entity level list, choose Domain. Select domains to up to 7 only in the Model Builder window. Under Results, select the datasets, click Revolution 2 dimensions. In the Setting window for Revolution 2 dimension, click the Expand the Revolution Layer section. In the Revolution Angle text field, type 360. In the Model Builder window, under the Results, click Electric Potential. In the Settings window for two-dimensional palette group, type electric potential without grading rings in the label text field and click Button Palette. You see we have a palette here. The surface shows electric potential based on the volt. For high voltage insulator, it is of importance to install grading rings at both ends of the insulator to make the electric field distribution more uniform. In the following, add the grading rings and then compare the electric field distributions. Now I want to go through the geometry with grading rings. Circle 2. In the geometry toolbar, click circle. In the setting window for circle, locate the size and shape section. In the radius text field, type h divided by 2. Locate the position section. In the R text field, type d divided by 2. In the Z text field, type d and circle 3. Right click circle 2 and choose duplicate. In the settings window for circle, locate the position section. In the Z text field, type 1150. Now I want to go through the electrostatics grading ring line N. In the physics toolbar, click domains and choose domain terminal. In